So with your chemical reactions, for the first two, you are not expected to be able to predict products. Okay? But for the first two, you're expected to still be able to balance them. Not only are you also expect to be able to balance them, but you also have to be able to identify them. So if I give you an equation, you should be able to tell me, oh, that's a combination, or that's a decomposition, just like with the one we've got up on the board. You look at that and you say, that's a decomposition. You should still be able to identify that. You don't have to predict what those products are going to be. Okay? With the single replacement, double replacement, and neutralization reactions, I do expect you to be able to predict those products. We haven't looked at those yet, okay, so it makes it a little bit more difficult for you to decide how difficult that's going to be because we haven't talked about it. Okay? For all of these, though, you need to be able to look at an equation and say it is that type. Okay? So having this general format memorized for what each of the individual reactions are can help you out because you will be expected to identify those individual types of reactions. Is that a hand? The name for this compound? Yeah, aluminum carbonate. Good job. Other questions? Okay. I had to slow this down a bit because the afternoon's a little bit slower than you guys. Did we get through all the combination in here? We move in the decomposition? I think we did. Okay. So we'll skip those examples. And we did the mercury oxide, right? Yes?
Yes.
Okay. So what we're looking at is our decomposition reactions in this case. So we start with a compound that disintegrates into the individual components. Okay, you'll notice that our sentence tells you all of that information. You're not expected to be able to predict what those products may be. And that's because you could get a variety of different results happening out of that. Okay, so you have to have some more information with you. So let's take a look at another one, or another type of decomposition. Metal hydrogen carbonates decompose to give a metal carbonate, water, and carbon dioxide. Okay? So if we go through and take a look at a question, what does sodium hydrogen carbonate decompose into? So to start off with, it might be a good idea to convert into a reaction equation. What information do we know? We know sodium hydrogen carbonate. Sodium has what symbol? Hydrogen has what symbol? Carbonate has what symbol? Okay. Good idea to make sure that the formula that we've written down is balanced. Okay. Variety of ways that we could go through and do this. Okay. I personally look at it and I see the complex ion carbonate bound with hydrogen and sodium. -2, +1, +1. It's balanced. So that's what I personally see. It's a little bit different from what we've talked about so far. So let's adjust it a little bit. What you guys have seen for sure is that hydrogen carbonate has what charge? A -1. Is it balanced? +1, -1? Yeah, it is balanced. Okay. What other information could we tag on with this? Oops. The question didn't actually state it. That's my bad. It should have said that. Solid. Okay. You'll notice that I typically put the phases as a subscript. They don't have to be subscript. The textbook puts them as normal typeface. They usually italicize them though. Okay. So just kind of be aware of subtle differences there. What are the products in this? So again, this is not one that I would expect you to do on an exam, but I've given you some information to help you predict this. What are our products? It says metal carbonate. What's our metal? Sodium carbonate. And what else? H2O and carbon dioxide, CO2. Okay? Before we go to balance the whole equation, we need to make sure our formulas are correct. Do we have to worry about the formulas for water and CO2? Why do we not worry about those formulas? There's a couple reasons we could do with that. You probably know the formula for water and CO2, so you probably aren't concerned about it in that case. Regardless, there's another more important reason why you don't worry about it. What type of bond do you have between oxygen and hydrogen? Covalent. What type of bond do you have between carbon and oxygen? Covalent. You are not expected to balance the formulas of covalent compounds. Okay? So the one we are expected to balance would be our sodium carbonate. What's the charge of sodium? Charge on carbonate? Carbonate is a -2. Okay, is it balanced? No. So what do we have to do to fix that? It has to become Na2, and that 2 comes in as a subscript right after the sodium. We do not put it out in front because then the 2 applies to everything after it. We use the subscript to apply the number to directly what's in front of it. Okay? Now that we have our formulas balanced, now we can go in and approach balancing the equation. Okay? I personally would probably erase all of my charge information just because it gets messy. And there are some professors that will give you a very hard time for writing your charge information in your final answer. Okay? I'll give you a little bit of leeway there, but be aware, at least when you're talking to me, I'll make you fix that. Okay? So, we now have our formulas we need to go through and balance. How do we start balancing? Start with anything except for hydrogen or oxygen. So we can start with sodium. How many sodiums do we have on our left? How many sodiums do we have on the right? Is it balanced? What do we do? Try to balance it. Good answer. We need 2 sodiums on the left. So we put the 2 out in front. Why do we not put it as a subscript? That changes the formula. Once we've established our formulas, we cannot change them. We can only put numbers as coefficients out in front of our equation. What do we move to now? So we've got a couple options here. Okay, I would personally push more towards the carbon end of the spectrum instead of hydrogen. Remember, hydrogen should be one of the last things you balance. I would actually take this a step further, though, and not balance just carbon. Take a look at the carbonate, the CO3. Does CO3 stay a complete unit? CO3 here to CO3 here. It does stay a complete unit. Okay? So I personally would balance based on the carbonate. I'm seeing some heads shake, saying no to that. Okay? Along those lines. It is absolutely going to work. There's nothing wrong with that. And to me, personally, I think the issue is coming from that we specified hydrogen carbonate was its own polyatomic ion, which is a load of crap. It's not. Okay? Do you want me to balance it with carbon or carbonate? I heard carbon. We'll stick with carbon. How many carbons do we have? Oh, good call. Why 2? The 2 in front applies forward. How many carbons do we have in the product side? Oh, I was looking at the small image. We have 2. Why do we have 2? We have 1 from the sodium carbonate plus 1 from our CO2. So we get a total of 2 carbons. What do we move to now? Okay. Not that big of a deal with this. If you have to advance further forward, you should balance hydrogen before you balance oxygen. Okay. Again, it's not a big deal, and if you really want to know why, you can talk to me after class about it. So, since I want to push that habit, how many hydrogens do we have? How many hydrogens do we have in our product? Coming from the water, our H2O. So our hydrogens are balanced. How many oxygens do we have? I only see 3. Where did you get 6 from? The 3 applies forward, the 2 applies backwards. We have 6 oxygens. How many oxygens do we have on the product side? Oh, man, I still can't add. What the heck? We get 3 from the sodium carbonate, 1 from the water, plus 2 from our carbonate, or sorry, our CO2, gives us a total of 6. Okay. What do we do now? Check it. How many sodiums do we have? How many sodiums do we have on the product side? How many carbons do we have? We got 2. How many carbons do we have on the product side? 1 and 2. How many hydrogens do we have on the reactant side?
2.
2 applies backwards. How many hydrogens on the product side? Again, 2. How many oxygens? 6 and 6. What am I going to tell you to do now? Check it again. It's already enough of a mess down at the bottom. I'm not going to do it again. Okay. Lots of back and forth. The back and forth, though, is ultimately, hopefully, just repetitive. Okay. Not more difficult, just repetitive. So if you go through and repeat your work, you should get everything balanced out okay. Questions about what we just went through and did? Yes?
How is it possible to balance it with carbonate when you get 2 new products on the other side? So you got CO2 and H2O.
Oh, the CO2. I didn't see the CO2. Never mind. You're right. You wouldn't be able to balance with carbonate. Yeah.
Yeah, I got
Good call.
one more question. Like right here, I did in the homework we have to predict the products at a few points, and I couldn't figure out how to predict it first, but then I found the rules for carbonate metals. So do we just need to memorize these rules right here?
So this goes back to what the textbook is going to ask you to do for practice and what I'm expecting you to do on the exam. What did we say on the exam for decomposition reactions? You do not have to have them memorized. Okay? So when it comes to the exam, I will give you the full equation. Okay? You have to then go through and balance it. Okay? For your homework, you have access to a lot more rules. So I expect you to take advantage of those rules. It's going to help you start to remember the patterns and how you go through and build these things. So the homework is definitely going to ask a little bit more of you than would be asked on the exam.
Well, I guess my question is, like, if you have a different molecule and then it gives, let's say, a different gas and a different liquid, or the decomposition products, how would you predict those without knowing the rules?
You wouldn't. So another chemist would, based on understanding more rules that are coming from how you generate different compounds and how compounds break apart. So someone that went through organic chemistry would probably be able to do those predictions.
Got it.
You're not expected to be able to do that yet. You're still on the CO3? Yeah. So yeah, let me announce that again for those at home as well. The carbonate you would not be able to balance. Yes, carbonate shows up on both sides, but you also have that CO2 showing up. If we tried to balance the carbonate on both sides, we would have no way to balance out the carbon in the product. Okay, so we have to go atomic in this case. We cannot do polyatomic ions. Same thing. Okay? Other questions with this one? Okay. Another one that we can go through and do, metal carbonates decompose to give a metal oxide and CO2. Okay. So this is a slightly different version, but now we're heating it up even further. So if we took our metal hydrogen carbonate, heated it up, it decomposes. We generate a metal carbonate. If we heat it up even more, it decomposes even further. Okay? How would you know that? There's a rule given to you. You have to apply those rules. So in the homework, you just have to look up those rules, or you pull to the slides where the rules are organized outside of the text, which hopefully makes it a little bit easier to find. So if we start with calcium carbonate, what happens? What is the symbol for calcium? What's the symbol for carbonate? Before we even start to predict our products, let's make sure our formula is balanced. Is that formula balanced? Calcium has what charge? +2. Carbonate has what charge? -2. How'd you know calcium was a +2? Second column on the periodic table. How'd you know carbonate was a -2? You had to have it memorized. Okay? Some things you got to have memorized, some things you can look up. So our formula is balanced. This decomposes with heat. How would we say with heat? Put a delta over our arrow. What does it decompose into? A metal oxide. What's our metal in this case? calcium, and oxide means just O. Don't worry about the O2 yet. That's a balancing our formula. We'll come back and look at the formula in a second. Just put a single atom in to begin with. Okay? And it decomposes into CO2. Of these two products, which one do we need to make sure is balanced? The calcium oxide. We do not need to worry about the carbon dioxide because it's a covalent bond. So we don't have to worry about balancing that one. So go to the calcium oxide. What's the charge on calcium? +2. Charge on oxygen? -2. How did you know calcium was +2? Second column on the periodic table. How did you know oxygen was a -2? That one's a little bit trickier to deal with. But if we go over to where oxygen is on the periodic table, if it gained 2 electrons, it looks like a noble gas. Most of your charges are coming from trying to get to being a noble gas, trying to make the electron cloud look like a noble gas. So oxygen will gain 2 electrons. Okay? Other way to know that it's a -2. Everybody's favorite, you memorized it. So now that we've got our formulas appropriated, I don't know why I used that word, but whatever. We need to go through and actually balance our formula. How many calciums do we have? 1. How many calciums on the right? Is that balanced? What do we do now? Why do we not do carbonate? Okay. We broke a covalent bond, is what I would go through. We don't see carbonate on the product side, so it definitely was destroyed. Okay. So how many carbons do we have on the reactant side? How many carbons do we have on the product side? Don't sound too enthusiastic. I know it's only 8 in the morning. It's actually 9 now. You should be awake. How many oxygens do we have? Reactant side? How many oxygens do we have on the product side? How did we get 3? Calcium oxide gives us 1. CO2 gives us the other 2. We've got 3 oxygens. What do we do now? Check it. So you go back through, make sure all your numbers match up and balance. Once you've got that, you say, yippee, I'm done. Okay? Yippee, I'm done. Believe it or not, if you start to make weird noises when you get it right, you'll probably see that you're going to start to get more things right. Okay? Kind of silly, but it works. Okay? And then you get people giving you weird looks, which is even better. Yeah?
Do we have to know that there was heat added?
No.
So the purple is a rule that always happens to metal carbonates.
Metal carbonates will always decompose in that fashion. Yep. Is that a rule you need to have memorized for the exam? No. Is that a rule you need to have memorized? Okay, you could memorize it, sure. Then your homework goes a little bit faster, but that's about it. Okay, you could have just as easily looked that up, so you don't have to have that memorized. Okay. New problem. Iron solid is mixed with aqueous copper sulfate solution. I guess I was a bit overzealous here and actually gave you the full equation. So we go through and evaluate. We've got our iron solid. So iron gives us the symbol Fe. Solid gives us our S. Our mixed with, we can color this. The mixed with gives us the plus. The next thing we see is aqueous, which gives us the AQ on our copper sulfate. Okay. We then see that we have copper, gives us Cu, and we have sulfate, gives us the SO4. I guess I could have colored that a little bit better. Okay. I'm not even looking at that quite yet, but we will evaluate that in a second. You'll notice in the course of this reaction, I gave you what the products were. Okay, why did I give you what the products were? Make this a little bit easier. We haven't seen an example of it yet, so I want to give you something that you can see to work with first. Okay? So what we would go through and do in this case, we now look to what happened to our products. What occurred as we went from reactants to products? What changed? Copper went from being combined with sulfate to now being on its own. So what we did is we replaced the copper atom with iron. We only did one replacement, so we've done a single replacement. Okay? As far as predicting these, what you would need to go through and do is identify, first off, one of the big characteristics for your single replacements is that you start with a metal in its elemental state. If you see that, you've almost instantly got an idea on what's going to happen with the exchange. You're going to be doing a single replacement, kick the other metal out of its complex, turn it into, go from an ion into a metal and put the iron in, or swap your metals. Okay? The next issue with this is going to be with balancing. Okay? I do expect you to be able to predict products in this to a certain extent. Okay? This is not one I would expect you to be able to predict the products on, though. Okay, why? What is the charge on iron all by itself?
0.
It's 0. Anything in its elemental state, so by itself, has a 0 charge. What is the charge in iron in the product? Okay, based on the formula given here, you should be able to predict that it's a +2. How do you predict that? Sulfate is a -2. The iron would have to balance it out. Okay, why is that a little bit tricky? If I didn't give you those products, you would put iron next to sulfate, and then you would need to balance it. What are the possible oxidation states for iron? Does it only have one? No, it has a lot. Okay? I would not expect you to know that. So I would have to give you a little bit more information. Okay? How would you be expected to be able to balance your final products? You'd be using a metal in the exchange that you know the charges for. For instance, if we did any group 1 or group 2 metal, why? What's the charge on a group 1 metal? +1 every single time. What's the charge on a group 2? +2. What if I gave you aluminum? You know it comes out as a +3. How about zinc or cadmium? Those you're supposed to know is a +2. Silver? +1. So I do expect you to be able to predict products when using those metals. When we use other metals, I don't expect you to predict the products because you don't know those charges. Okay? I don't know those charges either. Okay? So, let's go through and assume that this is correct. Now let's balance it. Where do we start with balancing? How many irons do we have? How many irons do we have in our product? Is that balanced? How many coppers do we have? How many coppers do we have in our product? Can I balance sulfates? Why can I balance sulfate as a unit? Okay. Doesn't change, and there's no other location of sulfurs in this. So I can balance with sulfate. How many sulfates do I have in the reactant? And sulfates in the product? 1. What do you do now? Check it. You go back and do it again. Okay? So yes, this equation is now balanced. We just talked about what type of reaction this was. We're looking at a single replacement. Okay? You will need to be able to predict these to a certain extent. I do fully expect that you should predict that the metals should swap, okay, as far as predicting the possible product, which is going to bring up a new issue here. Why do I say possible? Depends on if the reaction's actually going to occur or not. I can tell you right now that the textbook goes through and they say, look at this fancy table and then decide if it reacts or not, and if it doesn't react, say no reaction. I don't like that method because I have a very hard time interpreting that table. So what I do instead is balance the equation. Generate possible products and then evaluate with that extra information, the table. Okay? So we'll look at that method now. Like I said, I have a hard time with the table, so I can't even start to approach what the textbook is doing, okay? Because it just confuses the heck out of me. Yes? So your first step of prediction would be, what are the possible products? Everybody should be able to do that with every single equation I give you. The next issue is, does it actually form products? To do that, we have to know some more information. What happened to the iron in the course of this reaction? What was its oxidation state in the reactant? 0. What was its oxidation state in the product? +2. What was the oxidation state of copper in the reactant? +2. And the product? 0. Okay. What changed in this case? Yes, we changed the arrangement of atoms, but we also changed the charges. How do we change charges? We had to transfer electrons. Okay? It's that transferring of electrons that becomes a bit more challenging to work with. So what we would have to do is evaluate the two atoms that changed electrons. Did anything happen to sulfate? No. So I don't care about sulfate. It's there just to kind of balance charges out, and that's about it. But really what happened is a battle between iron and copper. And to me what that battle is which one wants its electrons more, or which one would prefer to be an ion. Okay? If we assume this reaction does work, we do make products. Okay? The conclusion that I would make is that iron wants to be an ion. Why would I make that conclusion? What did it start as? Not an ion. If the reaction works, iron becomes an ion. Okay? So that's how I would evaluate it. What wants to become an ion preferentially? Okay? How do we decide that? That's ultimately listed off in something known as the activity series. And since you're on that page, what are you, 7th edition?
Yeah.
Page 203 in the 7th edition, the lower right-hand corner, has an awful little table, which in my opinion is just confusing to read. Because now instead of a top to bottom, you have a top to bottom, left to right, and you have to do all this weird reading and confusion, and it's just silly. Okay? Well, it depends. If you got the slides, you can use the slides, and you don't have to look at that silly little table. Okay? This is another way to look at the activity series. The library has yet another version. Their version, again, I think is confusing because they double stacked it as opposed to doing a single column. Okay? What this activity series is telling us is ranking the ability of these individual metals in their desire to become an ion. Okay? So let's look at the extremes. Lithium up at the top and gold down at the bottom. Which of those do you think has the larger desire to become an ion? Why do you say lithium? Okay. The argument that I would make with this is if I throw gold into water, what happens? Nothing. Is that a good observation? Probably. Why do we use gold as jewelry? Because it doesn't react. It doesn't become an ion. Super, super stable. Okay? Whereas if I throw lithium into water, I make a big mess. Okay? I get all sorts of off-gassing of nitrogen. It's exothermic enough that it usually ignites the off-gassing of hydrogen. It's usually exothermic enough that it actually ignites the hydrogen coming off of it, and you get this big ball of fire and sparks and heat and all sorts of fun stuff. Okay? What's going on with that? Lithium really doesn't want to be a metal. It wants to become an ion. So the higher we are on this table, the more likely we want to be an ion. The lower we are, the less likely. When we go through and do a reaction, we don't evaluate just the height of one metal. We have to do it in comparison to what it's reacting with. So let's take this information back to our equation. What two metals do we want to compare with our equation? Okay. The way I evaluate is I look at copper ion and iron ion. The copper ion is on the what side of the equation? Left is valid. I don't want left, though. Give me a scientific word. We're looking at our reactants. And our iron is product side. Okay? What I'm evaluating are the ions in this case. Because to me, what I want to do is rank these according to their ability to become ions. So I'll now go back to my activity series and identify copper and iron. So where are we? Hopefully they're both on here. There's iron. There's copper. Okay? The higher up in the series means the more likely it wants to be an ion. Which is higher? Iron. So now I take that information and go back to my equation and say, whichever side of the reaction has iron ion is the side that is going to form. Where is the iron ion? On the product side. Should this reaction progress forwards? Yes, because iron is on the product. To get to the products, it must react. Okay? Kind of makes sense? Activity series. What should you do about that? To answer this question, you needed to know the activity series. Do you think I expect you to have it memorized? Okay. No, I do not expect you to have it memorized. As far as the test goes, I will supply you with a modified activity series. Okay? Probably not the whole thing just because there's too much stuff in there, but it's probably going to have more than you would use just to make sure there's some extra little confusion with it. Okay? Questions about that? Sure, I got at least a couple more problems. Good question. This activity series, you'll notice, ranks a whole lot of metals and then one hydrogen. Very, very odd. What's going on with that hydrogen being a non-metal in this? Okay. The hydrogen is kind of an odd circumstance, and we don't get a good example of why it's in there based on the activity series. What we're actually looking at is the ability of any atom to exchange electrons. Okay? This means nonmetals are part of this as well. Why do we not put nonmetals into this? Because it makes it more difficult to interpret, more difficult to read. What you'd be looking at is a reduction table. Not only would we have a ranking of these individual atoms, but we'd also throw in a whole bunch of extra numbers and calculations and stuff that you'd have to worry about in second semester Gen Chem 152. Okay? Why is hydrogen in there? Hydrogen is ultimately the 0 point to which we compare everything else. Okay? That is why hydrogen is there. You'll notice it doesn't look like it's a 0. It's not in the middle as far as our metals go. It's because it's not in the middle as far as the metals. Remember, if we look at all possible structures, we could look at a bunch of nonmetals as well. Hydrogen just happened to be our easiest 0 to compare everything to. Okay? So we had to come up with a standard to say, where does everything react around? And that's ultimately hydrogen. Okay? Not that big of a deal for you guys to know. Just realize that hydrogen can and will show up in individual reactions. Okay? And you should treat it like you would treat a metal. Okay? And we'll see 2 examples in these 2 problems, or a couple of these problems. So, first problem. If we were to predict the products, we're going to go through and do the exchange. What the heck? Why is that 2 there? Did I balance it for you? That's weird. I must just left it in by accident. Okay. Well, we're going to definitely identify our metal as our iron, but what's our other metal? I don't really see a metal. That's because in this case we're using hydrogen as our metal. Those 2 atoms need to swap. Okay? So we will end up making iron chloride, and then we need to have the elemental state for hydrogen, which is H2. Okay? Is our formula balanced? H2 is good, but how about iron chloride? Okay, how do you know it's not balanced? What's the charge on chloride? What's the charge on iron? Could be any number of different things. Okay? This is, again, not one I would expect you to fully balance out. I'd give you a little bit more information. In this case, I'm pretty sure We'll see if I'm right, that this is supposed to be iron 2 ion. Okay. Is that formula balanced? Nope. How do we balance it? We need 2 chlorides to balance out the 1 iron. So we've got FeCl2. Okay. Now that our formulas are balanced, we can go through and try and balance the equation. Irons on both sides equal 1 and 1. Chlorines equal, started to balance it for you. And the chlorine on the other side, hydrogen, 2 and 2. So our formula is now balanced with that extra 2 that I gave you in there. Okay? So now the next issue, once we've got our prediction set up, we need to evaluate, should this reaction actually occur? What were the 2 metals that we were comparing? Iron and hydrogen. So I would go back to the activity series. The higher on the activity series, the more likely it wants to be an ion. Which one's higher on our activity series? Iron. So now I go back to my equation and see, where is iron and ion? In the products. Does this reaction occur? Yes. To get to the products, we have to make that reaction pass along. So we do see a reaction here. This is what we would leave it with. Okay? Questions? Okay, let's try the next one. This is again a tricky one. Man, why didn't I pick any good ones? That was pretty awful. Let's take a look at the next one. We've got gold as one of our metals, and the other metal is hydrogen. Okay? So we want to go through and do our swap. We're going to end up with gold with the sulfate and hydrogen in its elemental state. Hydrogen in its elemental state happens to be H2. Where did that 2 come from? How did we decide that we needed a 2 there? See it. Okay, we're hearing a lot of different answers here. There is only one reason that 2 is there. That is because this is a single replacement reaction, and we form hydrogen in its elemental state. It must be H2. It is not because there is a 2 over here. That is completely irrelevant. Okay? We need to balance the formula first, then we can balance how many individual atoms there are. Okay? When we're doing the single replacement, we must put our element into its elemental state, and then we can go through and evaluate after the fact. Okay? A good example would be to look at that previous problem. How did we get H2 up here? Why was that H2? Its elemental state. It just so happened that then meant we needed a 2 in front of the HCl. Okay? But we have to put it into the elemental state first, then deal with balancing the reaction. Yes?
Do you have to put it into the solid liquid?
I'm sort of intentionally leaving those off. At this stage, no, because that information hasn't been specified to you. Okay? If I'd asked you to balance these equations, all I'd be looking for is that can you make that correct product? And we kind of go from there. Okay? So, yeah?
The book states that anything after hydrogen doesn't react with acid at all. Is that not?
So this is where the difference comes into play. Okay? I write out the full equation because that is absolutely possible. Now what I want to do is evaluate, after I've got my equation, did that actually occur or not? So that's the next issue. Okay? And it comes from, for me personally, the interpretation of the activity series. I have a hard time interpreting that for some reason. I just do. So I go based on the individual heights and say it wants to become an ion or it doesn't. Okay? So what I'm trying to do is separate the 2 concepts. I want to draw out a reaction first, then decide, is that reaction valid? What the textbook is having you do is start to draw out the reaction in your head, which you're going to get wrong. Okay? That's not your fault, that's just practice. And while you're drawing it out in your head, try and also do a second level of interpretation on top of it. Okay? You're stacking too much into an individual interpretation. If you get it right, great. If you can get it right consistently, you're better than me. I'm cool with that too. Okay? What I want to see is the full reaction first. Then you can decide after the fact, once you've got that balanced reaction, is it a valid one or not? Okay? Which we'll get to here in just a second. The next issue, what is the charge on gold? Okay. Technically it's a +3, but I don't really feel like balancing it, so let's just call it +2 in this case. Everyone okay with that decision? Okay, good, I like that. We're going to say gold is a +2, which means, is our formula for gold sulfate balanced? Yes. So now we could go through and balance our equation. Is our equation balanced? Do we need to work out balancing that equation? Hearing enough no's that I'm not going to do it. It is balanced as it is. Now we go back and evaluate our ion philosophy. I'm using the activity series. What are the two ions that I want to compare? I want to compare hydrogen ion and gold ion, sorry. So now I'll go back to my activity series and circle those two. Where are they? Hydrogen and gold. Which one is higher in the activity series? Hydrogen, which means hydrogen would preferentially be an ion or in a complex. So we go back to our equation. Where is hydrogen an ion? In the reactant side. What does that mean? Does the reaction progress forwards to form products? No, because hydrogen wants to stay with sulfate. It wants to stay in a complex. Okay? How the textbook then goes through and does this, again, I do think it's kind of frustrating. They go through and then say, okay, well, that means that this reaction didn't occur and all that balancing work is for naught, no reaction. Okay? Yeah, it is no reaction. The textbook will get you to the exact same conclusion. The issue is that you have to be able to interpret the activity series and balance your equation all very adeptly in your head. Okay? My argument is that I can't do that. I'm not going to show you how to do that because I can't do it consistently. So I would balance out the equation, go, oh crap, I spent 2 minutes balancing an equation, oh well. Okay? But I know it's no reaction because I've arranged those elements proper to each other. Yes?
I think I'm beating the horse here, but still an acid. The book said those things below hydrogen don't react with an acid.
So why does it not react with an acid? So the reason it doesn't react with an acid is because of the activity series. So what the book is giving you is a rule to memorize. So you could memorize an extra rule, or you interpret something which you're going to have every single time. Okay? So it's a question of how you want to spend your memory. I prefer to not spend my memory on something that I'm given. Okay? So it's the exact same conclusion. It's just a question of how you approach it.
Can you explain again? I know.
Let's do the last one. Okay? Last one. We predict. What do we end up with? We're looking at gold and copper. Gold would switch to gold sulfate, and we would end up with copper in its elemental state. Okay? Again, let's assume gold comes in as a +2 charge. Is our equation balanced? Yes. So now what I want to do, look at the two ions I want to evaluate. My copper in a complex or gold in a complex. So the interpretation that I would then go through and do is find them in the activity series. Gold is at the bottom, copper is right here. Which one is higher on the activity series? Copper, which means copper preferentially wants to be an ion, or in a complex, if you will. Where is copper in a complex? On the reactant side. What does that mean? No reaction. Copper started exactly where it wanted to be. We do not get a reaction here. Okay? So the activity series is ultimately a measure of how much it wants to become an ion. The higher on that series, the more it wants to be an ion. So go through, look at your equation, and decide where is it in an ionic state. Where is it charged? The only place that a metal can be charged is when it's bound to some nonmetals. Okay, so anytime we see a bond, we'll have a metal in its charged state. Okay? Angela, did you have a question?
Yeah, the book doesn't list platinum as on the list.
How many different metals are on the periodic table? A lot. So depending on different activity series, you will see different metals. It just depends on who wants to put what metals in there. Okay? In your exam, you are going to, again, see a different selection. Because I'm not going to do all 15 of those. I might just pick 5. Okay? What will not change, or what should not change when we look at the activity series, is the relative order. Lithium will always be above gold. Platinum will always be above gold. Okay? So in a general fun question here, you'll notice the last 3 metals are silver, platinum, and gold. Why do you think we might have picked those elements to be our standard for all currency? Because they don't change. Very difficult to disrupt those ions or those metals into an ionic state, which means if I have a brick of silver, it's going to stay a brick of silver for all eternity. If I take a brick of lithium and base my currency off of lithium metal, okay, someone could run by and throw water on it and then go, ha ha, you're poor now, okay, because you don't have any. Okay? So that's kind of the intent behind a lot of our currency systems, is we happen to pick metals that don't change their states. Why not mercury? Mercury's pretty low on that. Mercury's a liquid, harder to contain the liquid. Okay? Other questions with the single replacement reactions?
Is there a exceptional for these activity series?
Is there a what?
Exceptional? Sometimes, like, I remember magnesium is higher activity in the table than hydrogen, but it's shown no reaction.
Not true. It does show a reaction. When you mix magnesium with HCl or nitric acid or sulfuric acid, any acid, it absolutely does react.
So
When it's higher, it wants to become an ion every single time. Okay? Other questions? Okay. So I will definitely give you a condensed activity series on the exam. Do not spend your time memorizing that. Okay. So active metals and water. There are some metals that are very, very reactive and will also react with water. We are technically, again, doing a single replacement reaction in this case. It's just not quite as obvious. Is there another way that we could write out H2O? OH. There's our H+. Okay? That's the hydrogen ion that we're referring to. It just happens that there's a few metals where that hydrogen ion, or most metals, that hydrogen is not reactive enough, not positive enough for it to react with the metals. Okay? So it's kind of this weird exception. It's not even really an exception thing. We're just saying that some of those metals are just that reactive that they will react with pretty much any hydrogen that they can get a hold of. Okay? Why is that hydrogen partially positive? Because it's bound to our oxygen. Okay? That bond is relatively strong in this case in comparison to, say, something like H2SO4. So because the bond is a little bit stronger in water, most things won't react with it, won't quite break that. H2SO4 has a slightly different interaction. We will talk about what that difference is right at the end of the semester. Arguably one of the more important aspects for organic chemistry, actually.
So magnesium doesn't react?
There are certain metals that are active metals. I don't have them memorized. If I don't have them memorized, you don't need to have it memorized. Okay? We're just mentioning it because there are certain metals that do have this, exhibit this extra reactivity. Okay? So they are super active, not just active. Okay? What we're now going to do is kind of skip into chapter 17 for a little bit. I will say that some of this stuff can get a bit heavy. We're going to try and do it as simply as we can, but it's going to involve a little bit of mathematics, dealing with formulas and that kind of fun stuff. The reason we're bringing it in now is that when we went back to our single replacement reactions, what was the charge in our iron, in the reactant? 0. What was the charge of the iron in our product? +2. In the course of the reaction, we changed the state of iron by getting rid of electrons. Does anybody see in that equation electrons? No, we've kind of implied them. So what we need to do is come up with a way to see that implication and do an extra level of interpretation on top of it. So while these are all single replacement reactions, they also carry another special name. They are also known as reduction oxidation reactions, or redox. Okay? So that's what chapter 17 is looking at, is your redox reactions. Okay? I don't know why they, I guess oxygen comes before R, right? O before R, the alphabet. That's probably why they did that order. I think redox sounds better than ox-red. Okay? So what's happening with these? If we go through and look at a reaction, what we want to do is decide what changed within that reaction. Okay? Did I balance this one? Well, let's not ask it, let's check it. How many calciums are there on the reactant side? How many calciums in the product? How do you guys want to go through balancing this? Okay? We technically don't have to do this one separately, but I'm cool with doing it separately. How many hydrogens? 4. Why 4? 2 and 2. Hydrogens in our product. We get 2 plus 2. We're up at 4 again. Oxygens in our reactant. 2. You guys get in the habit of balancing yet? Some yeses, some nos, and 2. So yes, we do have this balanced. What's up?
How come you don't have to do it separately if it's broken up?
Let's write water slightly differently. Does the hydroxide ion change? No. So we could balance it based on hydroxides and hydrogen. Okay. In this case, it's not that big of a deal. It's not going to matter. Okay, but you could go through and balance it that way. Okay. So why is this important to look at? Well, sorry, not the balancing. Why do we look at redox? Well, what happened to the calcium? What was its oxidation state? 0. What did it become in the product? +2. Okay, how do we know it's +2? 2 ways to do it. What charge does calcium become in any complex? +2. So that's how we know one way. The other way is the charge on hydroxide. -1. How many hydroxides are there? 2. To balance it out, calcium has to be +2. Yes?
So when it says, when you say it's oxidation state, like what is the difference between...
We're going to get into what the difference is between oxidation state and charge. They are very easy to swap back and forth, and I would argue that most textbooks use them interchangeably. Okay? I use them interchangeably, and I'm trying desperately not to. Okay? So calcium changed its electronic state. It went from a 0 to a +2. In all reactions, though, we cannot create or destroy matter. What happened to go from a 0 to a +2? It lost 2 electrons. Are electrons matter? Yes. I cannot destroy them. Those electrons had to go somewhere. Where did they go? Something else had to pick them up. So what we would go through and do is determine the oxidation state, which we'll look at in a little bit, of all of the other atoms to see what other atom changed its oxidation state. Some of you were able to see hydrogen. What's the oxidation state of H2? Hydrogen in its elemental state. 0. What is the oxidation state of hydrogen in a complex? +1. To go from a +1 to a 0, what had to happen? It had to gain electrons to balance out that positive. Okay? So the electrons lost by the calcium went into the hydrogen. Okay? The next tricky part of this, +1 to 0, how many electrons did you need? 1. How many electrons did calcium give up? 2. That's still an extra electron floating around. How many hydrogens went? 2 hydrogens were converted across. Okay? That 2 is where we have to go through and balance our oxidation states. Okay? Make sure that when we balance our equation, we account for that charge. With the single replacement reactions, we can typically get away with not worrying about the charge because the ions that are also being exchanged in those cases, the anions, will balance our charge for us in most cases. Okay, so sometimes we don't have to worry about it. So oxidation state versus charge. Charge applies to a unit. Okay, what do I mean by a unit? Anything in an equation is a unit. All of these are units. Okay? The state, the oxidation state or number, only applies to an atom. So if I look at the oxidation state for a hydrogen atom in the unit of H2, that oxidation state is 0. If I look at the oxidation state for hydrogen in water, it's +1. For oxygen, it's -2. Maybe we should have done these in different colors so you can see that. Calcium metal, it was 0. Calcium ion, +2. Why is it easy to get confused? What's the charge on calcium ion? +2. I would argue that what we've called the charge on the calcium ion is not its charge, but its oxidation state. Why do we call it charge? How many of you panicked when I said oxidation state? Okay. There's kind of this barrier to, oh my God, that's a big word, that must be difficult. Okay. Whereas charge, we tend to understand a little bit more. It implies an imbalance of positives and negatives. Oxidation state removes all ability to kind of interpret it. Okay. So oxidation state is the balance of electrons on an atom. The charge is the balance of electrons on an individual unit. That unit could still be just an atom. Okay, so let's take a look at some examples. Actually, before we get that. So let's look at some rules. Any atom in its elemental state has an oxidation state of 0, okay, which we've already discussed. Okay? An atom by itself with nothing else and it's not ionic is 0. Okay? For a monatomic ion, the oxidation state equal the charge on the ion. So this is one of the reasons why it gets confusing, because the charge can equal the oxidation state. Okay? Nonmetals usually carry a negative oxidation state. Okay? If you think back to our charge rule, what charges do nonmetals typically carry? A negative oxidation or a negative charge. Oxygen will always have a -2 oxidation state. Yes, there's an exception to that. We won't worry about that in this class. Hydrogen will always be +1. Again, there's an exception to that. We probably won't see it. Okay? And then halides will always be a -1, except when bound to oxygen. Why when bound to oxygen? We started with oxygen being a -2 always, which means it doesn't matter what I attach it to, it is always going to be a -2. So if I put an oxygen on a halogen, the halogen has to adjust. Okay, it has to adjust to that oxygen. Okay? The sum, and this is where some math is going to show up, the sum of the oxidation numbers equals the charge of the molecule, which we will see, or the charge of our unit, specified in the upper right-hand corner. So when we go through and take a look at calcium solid, what is its charge? How do you know it's 0? There's nothing written in the upper right-hand corner. To determine the oxidation state, it's the sum of the oxidation states of all of the atoms, okay, multiplied by the number of them, okay? And that equals your overall charge. What atoms are in calcium solid? Calcium, what's its oxidation state? Well, at this point, it's X. Add in all the other atoms. How many other atoms are there? Just that one. So that then equals the charge. What's the charge? 0. What's the oxidation state of calcium solid? 0. Rule number 1 we just derived. What happens when we get to water? What is the overall charge on water? How do you know it's 0? Upper right-hand corner, there's nothing written, which means the charge is 0. If we now want to figure out, say, the oxidation state on hydrogen, we would then go back to our equation and say, okay, I don't know its oxidation state. How many hydrogens are there, though? 2. So I could either do X plus X, or I could write 2X. Plus the oxidation state of the oxygen. What's the oxidation state of oxygen? -2. How do we know it's a -2? That is our rule. Oxygen is always -2. That has to equal our overall charge. What's our overall charge? 0. How do we know it was 0? Upper right-hand corner of our formula. Solve for X. What does X equal? 1. What's the charge typically on hydrogen? 1. What's its oxidation state? Also +1. Okay? Yes, I did pick some easy examples there. So let's take a look at separating our definitions. If we want to evaluate charge, it's the number written in our upper right-hand corner of all formulas. Okay? Our oxidation state looks at the ion imbalance or the charge imbalance within a single element. Okay? So we've got the exact same examples for both of these. And we're going to have to evaluate, and yes, we will end on this. We'll have to evaluate what's happening on these. What is the charge for copper? How do you know it's 0? If we look at the upper right-hand corner, what is written there? I didn't time this very well. Nothing's there, so it's 0. What's the charge on copper ion? +2. How do you know that? Upper right-hand corner, it says +2. What's the charge on nitrate? -1. How do you know that? Upper right-hand corner. How else do you know that? You memorized it. Remember, nitrate's one of those ones you had to have memorized. Sulfate, what's the charge? -2. So those are our charges for each of those complexes. If we now go through and look at the oxidation state, what's the oxidation state for copper metal? Did I step this next part? 0. The charge and the oxidation state are the same for copper. Did I step it? Whoops, shoot, I didn't step it. How about the charge for copper ion? +2. What's the the oxidation state for nitrogen? How do we determine the oxidation state? I heard a lot of -3s. -3 is true if it's bound to a metal. Is it bound to a metal? No, not -3. Try again. +5. What? How do we do that? Well, do you know what it is? No, so call it X. How many nitrogens are there? 1. So 1 times X. Plus, what's the charge on oxygen? How many oxygens are there? What does that need to equal? Our equation equals the charge, which is -1. How do we know the charge was -1? Upper right-hand corner says it's -1. Okay? Solve for X. We get X minus 6 equals -1. X equals +5. Okay? The oxidation state for nitrogen is +5. For oxygen, it's -2. So what we would have to do for our oxidation states is apply it per atom, not per molecule. So all those charges that you memorized, there's really only 2 that are going to work for oxidation states. Those 2 are oxygen and hydrogen. And even hydrogen can get a bit questionable. You should be able to go through and do sulfur and discover that it's a +6. We will start with the next slide. Yeah, we'll go with the next slide on Thursday.